Okay, so we'll continue with the study of convergence in measure. So the previous session, what we did was we defined what is convergence in measure, what is Cauchy in measure, and then we studied its relationship with the pointwise convergence. So if it converges in measure, then you have a subsequence which converges pointwise, and if it is a finite measure space, then pointwise convergence always implies convergence in measure, and not true for infinite measure spaces. And we also saw that the limit was unique in the sense that if you have two functions to which a certain sequence converges in measure, then the two have to be equal almost everywhere, and that's as good as uniqueness. So that's as far as you can go because of the very definition of convergence in measure. Today we will look at the connection with almost uniform convergence, and also what is Cauchy in measure and convergence in measure, that they imply each other. Okay, so these are the things which we want to do today. So we will start with the following proposition. So excess mu measure space Fn sequence of real valued measurable functions. If I don't say this, please assume it always when we'll all talk of real valued measurable functions. Okay, then if Fn converges in measure, then it is Cauchy in measure. So this is always the easy part, so proof. So let us take Fn converging to F in measure, and then if you take, so let us take epsilon greater than or equal to 0, then set of all x in x such that mod Fnx minus Fmx is greater or equal to epsilon is contained in set of all x in x such that mod Fnx minus Fx is greater or equal to epsilon by 2 union set of all x in x mod Fmx minus Fx is greater or equal to epsilon by 2. This is the usual argument we gave, because this set is contained in, because the triangle inequality Fn minus Fm is less than Fn minus F plus F minus Fm, and then if each of these is less than epsilon by 2, so obviously this will be less than epsilon. So if this has to be greater or equal to epsilon, then it has to belong to one of these two sets. So given delta positive, so find n such that mu of mod Fn minus F greater or equal to epsilon by 2. I am writing it in short form here. This entire set is less than delta by 2, and mu of mod Fm minus F greater or equal to epsilon by 2 less than delta by 2 for all nm greater or equal to capital N. So this will imply then mu of mod Fn minus Fm greater or equal to epsilon is less than delta for all nm greater or equal to capital N, and that proves that is Fn is Cauchy in measure. Okay, so now we have to do the converse. That takes some work, and it also gets mixed up with the question about almost uniform convergence. So we will, proposition, we will do it in several stages. Okay, excess mu measure space Fn sequence of real valued functions Cauchy in measure. So our ultimate aim is to show that this converges in measure. So if there exists a subsequence Fnk which converges in measure to real valued measurable function f, then Fn also converges to measure to f. So this is just like in real sequences. You have a Cauchy sequence, and if you have a convergent subsequence, then the original sequence is also convergent and it has the same limit. Okay, so proof. So let epsilon be greater than 0, then set of all x in x such that mod fnx minus fx, it's the same argument, greater or equal to epsilon. This should be contained in, I won't explain anymore, set of all x in x such that mod fnx minus fx fnkx greater or equal to epsilon by 2 union set of all x in x such that mod fnkx minus fx is greater or equal to epsilon by 2. We are repeatedly using. So then let delta be greater than 0. So there exists a capital N and such that for all n bigger than or equal to capital N and nk greater to capital N, we have mu of mod fn minus fnk less than delta by 2 and mu of mod greater or equal to epsilon by 2 fnk minus f greater or equal to epsilon by 2 less than delta by 2. So this is because of the convergence in measure of the subsequence, and this is because it's a Cauchy subsequence. Therefore you have mu of mod fn minus f greater or equal to epsilon is less than delta, and for all n greater or equal to capital N, that is fn itself converges to f in measure by the definition of convergence in measure. Okay. Proposition. So our aim will be, if you have a Cauchy in measure, we will try to construct a subsequence which is convergent in measure, and then the original sequence will also converge. So excess mu measure space fn sequence of real valued measurable functions converging almost uniformly to f measurable real value, then fn converges to f in measure. So if you have almost uniform convergence, then you have convergence in measure. So proof. So let epsilon greater than 0, then you and let delta also be greater than 0. So choose f in S, mu f should be less than delta, and on f complement fn converges to f uniformly. What does it imply? There exists a n naught such that for all n greater or equal to n naught, and for all x in f complement, you have mod fn x minus fx will be less than epsilon. So for all n greater or equal to n naught, you will have, so this depends on epsilon and really on delta also, because you are using the delta comes because the choice of the set f and then therefore f complement. Epsilon is because of the uniform convergence on f complement. So we have this, that mu of set of all x in x such that mod fn x minus fx is greater or equal to epsilon. So that cannot be in f complement. So this is less than or equal to mu of f, which is less than delta, and therefore this proves that fn converges to f in measure. Next proposition, xs mu measure space, fn real valued measurable functions, Cauchy in measure. Then there exists a subsequence which is almost uniformly Cauchy. So you now see how we are going. So we have a sequence which is Cauchy in measure. So you have a subsequence which is almost uniformly Cauchy. Now almost uniformly Cauchy means almost uniformly convergent. We have already seen that. And almost uniformly convergent implies convergence in measure. So what we have done is we have seen that there exists a subsequence of a Cauchy in measure which is almost uniformly Cauchy, therefore almost uniformly convergent, therefore convergent in measure. And then by the previous proposition which we proved, you have a subsequence which converges in measure, and its Cauchy in measure means it converges in measure to that same function. Okay, so that is how we are going to prove, and in that process we are proving also results connecting convergence in measure and almost uniform convergence. Okay, so proof. So let k belong to n, then there exists a nk in n such that for all nm greater or equal to n of k, you have the measure of the set of all x in x such that mod fnx minus fmx greater than or equal to 1 by 2 power k can be made as small as I like. So I am going to make it less than 1 by 2 power k. Now you choose n1 equals n of 1 plus 1, n2 equals max of n of 2 and n1 plus 2, n3 equals max n3 plus n2 plus 3 and so on. So nk equals max of n of k and nk minus 1 plus k. So nk is greater than nk and nk is bigger than k also. So therefore we have nk is a proper subsequence. Fnk is thus a subsequence. So now we will define Ek is set for x in x such that mod fn kx minus fn k plus 1 x is less than, greater than or equal to 1 by 2 power k. But nk plus 1 are all bigger than the n of k, and therefore by this condition here, so this implies that mu of Ek is less than 1 by 2 power k. You connect with these conditions, this condition, so that gives you this. So let delta be greater than 0. Choose k such that 1 by 2 to the k minus 1 is less than delta. And you set f equals union I equals k to infinity ei. Now what is f complement? This is equal to intersection I equals k to infinity ei complement. So what about mu of f is less than or equal to sum of mu of ei. So sigma I equals k to infinity mu of ei. Mu of ei is less than or equal to 1 by 2 power I, and so that's a geometric sequence, and therefore you have that this is less than 1 by 2 power k minus 1 using the fact of this, and that of course is less than delta by choice. Now also you choose epsilon. So given epsilon positive, choose n bigger than or equal to k and 1 by 2 power n minus 1 less than epsilon. So now you take x in f complement, that means it's in all the ei complements, and then you take m greater or equal to L greater or equal to capital N. N is bigger than k already, so we have this, it's in these sets, and therefore if x is in E complement, it's in all of these sets here, and n, m and L are bigger or equal to n, which is bigger than k. Therefore I get mod fn L of x, fn minus fm n m of x. I am going to write this by triangle inequality. This is equal to j equals L to m mod fn j of k minus fn j plus 1 of k of x. So it's in each of these is in the corresponding ej complement, and therefore this is less than sigma j equals L to m 1 by 2 power j, and that's equal to 1 by 2 power L minus 1, but L is bigger than n, this is less than 1 by 2 power n minus 1, and that is less than epsilon. And therefore this is true for all this, and therefore you have fn k is uniformly Cauchy in f complement, and mu of f is less than delta. Okay, so this proves that you have a subsequence which is almost, so fn k is almost uniformly Cauchy. Now we are almost home. So proposition XS mu measure space, Fn real valued measurable functions, Cauchy in measure. This implies there exists a real valued measurable function f such that Fn converges in measure to f. So Fn is Cauchy in measure, so Fnk almost uniformly Cauchy implies there exists an f such that Fnk converges to f almost uniformly, and that implies that Fnk converges to f in measure because we have proved that, and because you have subsequence which converges in measure and the original is in Cauchy, so this implies Fnk converges to f in measure. Okay, so now we have proved a lot of things, so it is better to have an idea what we have proved. So we have convergence almost everywhere, then we have almost uniform convergence, and then we have convergence in measure, and then we have that almost uniform convergence is the same as almost uniform Cauchy, and then convergence in measure is the same as Cauchy in measure. By this I mean if you have a sequence which is almost uniformly convergent, then it's almost uniformly Cauchy. If it's almost uniformly Cauchy, then it's almost uniformly convergent. Similarly, convergence in measure implies it's Cauchy in measure. Cauchy in measure implies convergence measure. So these we have proved. Now convergence almost everywhere and convergence almost uniform convergence implies convergence almost everywhere we have seen. Almost uniform convergence also implies convergence in measure we have seen. Now convergence almost everywhere implies almost uniform convergence provided the measure is finite. Similarly, convergence almost everywhere implies convergence in measure provided the measure is finite. Now convergence in measure implies almost uniform convergence for a subsequence, because we found that there is a convergence in measure means Cauchy in measure. Cauchy in measure means there is a subsequence which is almost uniformly Cauchy and therefore almost uniformly convergent. Similarly, convergence in measure also means convergence everywhere for a subsequence. So these are the various interrelationships which we have. Now if you have a sequence which is convergence in measure, the subsequence which converges almost everywhere, we showed using the Borel-Cantelli lemma. But you can also now do it this way. Convergence in measure means there's almost uniformly Cauchy subsequence, which means almost uniformly convergent subsequence, and that subsequence will imply of course pointwise everywhere, and therefore this is another proof using these two arrows which you can do for that particular theorem. So now we want to do what is a relationship of convergence in measure to the algebraic operations alpha fn plus beta gn, where fn gn are convergence in measure. What is fn gn, and then what about mod fn and such things, and therefore we will see those things next time.